Pipelining and hazards. Pipelining hazards are situations that prevent the next instructions in the instruction stream from executing its designed clock cycle. Hazard reduce the performance from the ideal speed of gained by pipelining. It is a three types of hazards: structural hazard, data hazard, and control hazard. Structural hazard arises from resource conflict. The hardware cannot support all possible combination of overlapping instructions. Data hazards arise when an instruction depends on the result of previous instructions in a way that expects overlapping of instruction pipeline. Control hazard arise from pipelining of branches and other instructions that changes the PC. Hazards in pipelining can make the pipeline to stall. Eliminating the hazards often require that some instructions in the pipeline to be allowed to proceed while other they delay. When instructions is stalled, instructions issued later than the stalled instructions and stopped, while the ones issued earlier must continue. No new instructions fetched during the stall. In certain combination of instructions cannot be accommodated because of resource conflict. The machine said have structural hazard. It can be generated by some functional unit not fully piped. Some resource has not been duplicate enough to allow the combination of pipeline to execute. For example, say a machine have only one register 5 write port and but under the certain conditions the pipelines might want to perform two writes in the one clock cycle. This will generate a structural hazard. When sequence of instructions encounter these hazards, the pipeline will stall one of the instructions until the required until the is available. Such stalls is increased clock cycle per instructions for ideal high prepared missions. A missions with a structural hazard will have lower CPI. Why designer allows structural hazard to reduce the cost. Pipelining all functional units duplicate them may be too costly. To reduce latency, introducing too many pipeline stages may cause latency issues. Data hazards occurs when the pipeline changes the order of read, write, access, and operating that the order differs from the orders in sequential executing instructions on the pipeline machine. Consider the execution following instructions on our pipeline example process. Add R1, R2, R3, sub R4, R1, R5, and R6, R1, R7, or R8, R1, R9, XOR R10, R1, R11.
In the IO diagram, the x-axis tells about the clock cycles time and the y-axis tells about the program execution time. In that diagram, we can see there are multiple registers and arithmetic logical unit and direct memory and indirect memory. The use of results from add instruction causes hazard since the register is not written until after those instructions read it. In the second diagram, the x-axis shows about the clock cycle time of the registers and y-axis shows about the program execution order, and there are multiple various operations performed. They are addition, subtraction, and or XOR. Eliminate the stalls from the hazard involving subtraction and instructions using a technique called forwarding. In the third diagram, x-axis shows about the time in clock cycles and y-axis about program execution order in instructions. Here the instructions performed are add R1, R2, R3, load R4, 0 of R1, SW12 of R1 dot R4. Here there are multiple registers ALU and IM. Store requires an operand during MEM and forwarding in shown here. The result of load is forwarding from the output in MEM/WB to the memory input to be stored. In addition to ALU output is forwarded to ALU input for address calculation for both load and store. Control hazards. These can be cause greater performance loss than the data hazards. When a branch is executed, it may or it may not change the PC to other value than its value plus 4. If a branch is changing to the PC to its target address, then it is a taken branch. If a branch does not change the PC to its target address, then it is not a taken branch. If instruction I is a taken branch, then the PC value of will not change until the end of MEM stage of the instruction execution in the pipeline. A simple method to deal with branches is to stall the pipe as soon as we detect a branch until we know the result of the branch. Here is the table of control hazards. Here are the branch instructions IF, ID, EX, MEM and WB and branch successors. For ID, branch successor is IF. For EX, branch successor is stall. For MEM, branch successor is stall. For WB, IF, branch successor plus 2 and branch successor plus 2 are the below tables. A branch causes 3 cycles stall in our example processor pipeline. One cycle is repeated if necessary if the branch should be taken. If the branch is not taken, the IF is redundant. 2 cycle idles.
Control hazards. The 3 clock cycles last for each branch is a significant loss. With a 30% branch frequency, the machine with branch tail achieve only about half of the speed of from pipeline. Reducing the branch penalty becomes critical. The number of clock cycles in a branch stall can be reduced by 2 steps. Find out if the branch is taken or not in early stage in the pipeline. Compute the taken PC earlier. Modified pipeline instruction fetch. Instruction fetch. Here are some instruction fetches and operations. Send out the PC and fetch the instructions from the memory. Increment the PC by 4 to address to the next instruction or save the address generated by a taken branch of a previous instruction in decode stage. Again instructions decode cycle, you can see here, and their options are decode the instruction and address register files to access the registers. The output of the general purpose registers are read in two temporary registers A and B, part of the pipeline registers ID or EX stage for use in later clock cycles. The lowest 16-bit of IR stored in pipeline registers from IFID stage are also sign extended stored into temporary register IM for later use. Value IR is passed to the next stage of pipeline registers. Compute the values for the cond and branch target and use them to set the PC if necessary. Thank you.